share my screen. Give me 1 second here to pull something up. Sorry about the holdup. My signal on my pad that I use is running real slow for some reason. All right. All right, so this week, the overall rationale behind this module is that we're going to spend a whole week on data structures, and you could spend a whole lot more time on data structures because it applies to the real world. It's real world stuff. It's CS that matters. And the best data structure, a lot of times people always ask, well, what would be the best? Or what is the best? A common question for a lot of things. And the answer is the best data structure for the specific project or application you were working on will depend on its unique specifications. So it's going to depend on what we need and the parameters and the restrictions that we have that will lead us to choose the best data structure. During this sprint, we'll be talking about common operations like insertion, deletion, access, search, etc., and work with the different data structures. And this will help you understand when you might choose one data structure over the other for different projects. So the takeaway from all of it is to be able to understand how we can utilize data structures such as an array, stack, queue, linked list, tree, and heap in Python, and talk about the operations that we just mentioned and how they're implemented for each data structure. And we will talk about the runtimes of the aforementioned operations on various data structures. So touching on runtime again, we'll also talk a little bit about space complexity because that will really come into play next week. So hopefully everybody was at least able to watch the first two videos that I dropped over the weekend and then posted again today over the queue and the linked list. I'm aware that you've already worked with a lot of these data structures, so hopefully everyone has a really good understanding of the 40,000 foot view of them. And now that we dive into their guts, you know, that'll be the part to tackle as far as learning and working with. So we're going to take a moment and we're going to talk about the different types of data structures that we will be dealing with this week. We're not going to spend a whole lot of time on any of them. This information is in the training kit in this section that is student facing for you. So I'm going to go through this kind of quick so we can spend more time on the code and more time with interactive things. And we'll be implementing a linked list and some singly linked list and some very basic methods on that singly linked list. So the first data structure are arrays, and arrays are a linear data structure. We can access items located anywhere in the data structure using numerical indices, just like the bracket notation we used in JavaScript, the same notation we use to access an index in Python. And this allows us to access a specific element given that we do know the index that it's at in constant time, one time. We don't have to iterate through the entire array searching for it. We simply go right to that element, but we do have to know the index that it's at. The runtime of inserting and deleting items into an array are not as optimal. And this is a really important point right here. For what's coming up and just an overall understanding of what's going on under the hood with arrays and why their runtime is not optimal. And the problem with that is during an insertion. So this is that I've got pulled up here is actually a linked list, and we will use that in a second. But just imagine that each of these was an element in an array. So you had index 0, index 1, index 2, index 3. And the problem with insertion is that to create space for the item being added, everything to the right of its target must be shifted over by 1 in terms of the memory pointer, the index that it's at. And if we are inserting an element into the beginning of a very large array, because we have to shift everything over in the entire array, you could have close to the entire length of the array, the n of the array, consumed in that operation. So the runtime would be O to the n because everything in that array is having to shift over to the right and increment up 1. And the same with deletion. To fill the gap created by an item that we removed, everything to its right must be shifted over by 1. And it's the same if we're deleting an element from the beginning of a very large array, we could have close to n operations that occur. So always keep that in mind, that when you're dealing with an array as a data structure, that a lot of, if you can think of it in terms of, do we have to iterate over or move items in the entire array? And if we have to do that, you're going to be at O to the n time immediately. So we know that while that's not the worst time, that's not ideal. So more on that later on. Stacks are a linear data structure that follow last in, first out. And a real world example would be, let's say, a pile of paper sitting on your desk, or a stack of dirty dishes building up to be washed. The last piece of paper or the last dish that went on there will be the first piece of paper that eventually, or the first dish that gets removed. So a few things that I'm sure you're aware of, but we're just going back over, that a few named operations specific to stacks are push, and that's adding an item to the top of the stack. Pop, which is removing the item on the top of the stack, typically returns the item that is removed. So same as what we did in JavaScript, same as what happens in Python, that when you remove an item with a pop, the return value is that item. When you push an item, I can't remember in JavaScript, when you push an item in JavaScript, I don't remember if it returns the entire array or if it returns nothing, but definitely the pop is the same. And also there's something called peek that you might not be aware of. It's not so commonly known as, but that's returning the value of the item on the top of the stack without removing it. So a very similar operation to the pop, but you're simply not removing it, but you're having to access it and give the return value of it. Queues are a linear data structure that follow first in, first out. A real world example would be a checkout line at the grocery store, or a line at the bank waiting to see the teller. The first person added to the line is the first one that gets to exit the line when there's an open space. So a couple of named operations specific to queues are onQueue and dequeue. OnQueue being adding an item to the end of the queue, the back of the line, or dequeue, removing the item at the beginning of the queue, and it typically returns the item that is removed. Kind of a real quick summary of what the difference between a stack and a queue is that we add and delete to the same side of a stack, while we add and delete from opposite sides of a queue. So when you're adding and deleting on the same side, that means that's why you get that last in, first out, because the most recent that has been added is the first thing that we can remove. Whereas in the queue, we are adding and deleting from opposite sides, so we don't run into the same problem that we do with the stack, that you have to take the items back off one by one if you're trying to access the back of the array. So different situations, different ones will be advantageous, as we will see later in the week. A few questions that I'm going to throw out to kind of break up the monotony of me talking and just to get the group involved. What do you think the runtime of accessing an element on a stack or a queue is? Somebody talk. The runtime of accessing an element on a stack or a queue. See somebody typing. O to the 1. Anybody else have any guesses? Anybody else? So it's actually O to the N time. Anybody have any thoughts on why that may be? I guess let me reword it a different way. Maybe I didn't word it quite good. The runtime of accessing an element on a stack or a queue, if you do not know the specific. I'm wording that badly again. Yeah, the runtime of accessing an element on a stack or a queue is in time, because the way that we access those, think about, we talked about just now the on queue and the dequeue and the pop and the push, that depending on what you're trying to access, it can be close to in time. And the same for searching for an element or a stack or a queue. Anybody have any thoughts on what searching for an element on a stack or queue is? Let's see, Yanrong is typing. O to the N. Yeah, it's the same as basically accessing an element, because we might have to dig down that pile, or if that element went in last and we're in a queue, then that's going to take a while for that element's turn to come up. So the same thing, depending on where it is, and the same with any type of search, whether it's in an array or whether it's in a queue, whether it's in a stack. It's going to be overall in time, because if you had to access something at the very end and you're having to go element by element and iterating over it until you find the element you're searching for, it's O to the N time. How about inserting an element on a stack or a queue? Inserting an element into a stack or a queue. Inserting or deleting, and I see you said O to the 1. And it's actually O to the N as well, because to be able to insert or delete something, you've got to access it. And to be able to access it, think about the same thing that we've been talking above in a search, or simply like the first question in accessing it. So they're all O to the N time on average, which is what we use for Big O. Did someone have a question? Sounded like someone had their mic on.
Yes, I have a question. When you talk about inserting, are you talking inserting in middle of those, or are you talking inserting at the end of their?
Yeah. If I guess I didn't make that specific. If I'm talking about being able to insert items into the middle, yeah, it's definitely if you're just popping or pushing onto the queue or this. Is that what you're meaning?
Yes.
Yeah, that is O to the one time.
Okay. Great.
Sorry if that wasn't clear. These could have been worded a little bit better, and I apologize about that. But think about it, to access an element on a stack or a queue, you don't know how far you're going to have to get through it. And depending on which one we're dealing with and the last in, first out, first in, first out, you may have to go through almost the entire stack or queue. Same for a search. Same for inserting or deleting, unless we're talking about specifically on queue, DQ, stack, pop. Any questions? I said stack pop, push pop. So what we're going to talk about now and what we're going to give me 1 second. For some reason, again, my pad's moving slow. Okay. Can somebody type, is my voice and my screen share when I do move around, is it all transmitting well with no problems? Because I'm having problems with the tablet that I use and it's on the same network. So just wanted to check that. Yeah. All right. Well, I apologize. Let's see. Esteban was typing his. Cool. Yeah, I just wanted to check that it was going well. Normally somebody speaks up, but I thought it would be remiss not to at least ask at this point because I had the same problem with my tablet, but I don't exactly know. It seems like there's a drag in the network here. But a linked list is what we've got up here. This is a singly linked list. It's a linear data structure. Unlike arrays in which any item can be accessed. Now remember, we're talking about stacks and queues, and stack and queue is based not on a specific data structure used to implement it, but on rules. First in, first out, last in, first out. So now we're talking back about comparing this to an array, which we are well aware of and we introduced first. A linked list, unlike arrays in which an item can be accessed directly by its index, items in a linked list do not have an index or position. They only have a reference to the next item. And because of this, they can only be traversed in one direction. As we're shown here, and with the single arrows, this is always a representation of a singly linked list with a null pointer at the end. We'll get more into that in just a second. Like I said, they do not have an index or position. Yes, and the reason it's called a pointer, and you'll definitely get all into this in C, is because it's actually a pointer to a space in memory to the next item in the linked list. And that doesn't necessarily, unlike an array, which has a chunk of memory that it takes up in C. Let's say, for example, in a linked list, those bits of memory can be everywhere. So you have to have the pointer to it to be able to access it, because you just can't jump to the next space in memory and expect to have it there, because it won't be there. So yes, it's a pointer to a space in physical memory. The pointer, or yeah, good point, Yanrong. There are doubly linked lists, which they can be traversed in both directions, and that would simply be represented if you added an arrow here on each element, and you had a null pointer here at the end. They have nulls at both the head and at the tail, and it points in both directions. So to access C, you would have to, Jawad, you would have to start at the head. Okay, so we're at A, and then you're going to have to jump. A has a memory reference to B. So from A, we can go to B. And then from B, we can go to C, because B has a reference to C. A has a reference to B, B has a reference to C, the next reference that we'll see in the code here quickly. There is no reference back from C to B. C doesn't know where it came from. B doesn't know where it came from. Only A knows B, B knows C, C knows D. D knows the next place, which points to a null. Jawad, does that make sense? Good questions being asked, by the way. And I'm glad to hear y'all asking these, because this, like I said, is what we're covering in a lot of detail and with the code today. And these are important because you will utilize these both later in the week, let's say, when we do hash tables, for example. One common implementation of dealing with a major problem with hash tables, collisions, is using a linked list. And it's very specific to that, and it's instrumental that you understand how a linked list functions and kind of the ins and outs of a linked list to know why you're using it and understand how it works in relation to the. It's really not so great of a mystery, but everyone, a lot of people think that hash tables are like a holy grail of programming, and they're really a pretty simplistic thing once you understand them. But more on that later in the week. So definitely keep the questions coming, because these are relative to your assignment today in the independent project, and through the week and through the rest of computer science, and very well may come up on an interview, and stuff that's applicable to the real world. So definitely, worth noting that. Like I said, doubly linked lists can be traversed in both directions, but we will cover that variation later in the sprint. So these, I was referring them to elements, but these are actually referred to as nodes in a linked list. Anyone want to give me just a general off the top of their head definition of a node? Doesn't have to be the technical definition. What's a node? What is a node? Anybody? Yeah, a basic unit of a data structure. It's in this case, the piece that makes up a linked list. Thank you, Jawad. And like I said before, at times when I ask a question, I'll just sit and let the silence kind of hover for a while if nobody's going to answer. At least somebody hopefully is sitting there Googling something. Not saying that you did, Jawad, but just in general, I'm willing to sit at times and wait for an answer. So much appreciated. The response. But yeah, it's a data point. It's the basic unit. I always, in my head, if you just asked me and I just spit something out without thinking, I'd say a data point, and that's just individually how I think of it. But yeah, basic unit of a data structure, pieces that make up a data structure, and let's see what Yanrong is typing. Node is data and the reference of next data. And for specifically for this, yes. In general, a node is just a data point, a basic unit. In this case, with the linked list, yes, it's the data, the value, and the reference to the next data. But let's say in a doubly linked list, there's also a reference to the previous. So you would have three different things there, both the reference, the previous, and the next. So I just want to be real clear on that you are correct for specifically the singly linked list. And that's actually the next thing I was going to get to, are the attributes of a node in a singly linked list, and that's the value. That's the number, the string, the object, whatever's being stored in the node, whatever primitive data structure or other data structure is, or excuse me, whatever primitive or whatever other type of object or data structure is being stored in that. It can be anything, but that's your value. Like he's saying, node is data and the reference of next data. And the next, indeed, for the node attribute is the pointer to another node. And like I said, it is none or null if a node is last in a particular list for this particular data structure, as we see here, the null. So what are the names of the two nodes in our linked list that comprise the beginning and the end? What are the names of those for a linked list? One of them's on the screen. Head and tail, yep. The head and the tail. The head is the first node in a list. Be careful with that. Let me iterate over that at least once, maybe again. The head is the first node. For some reason in my brain, and I know other people have done this, I got it stuck in my brain that the head, because it's at the lead of something, and I always thought the head was what we were building onto. And I made this mistake back when I was a student, and it took me a while to get that straightened out. And I've seen a lot of people that maybe didn't get that through their head right away when they were covering this. They ended up being confused by it later. So the head is the first node in the list right here, the beginning of the singly linked list. The tail is the last node. And of course, we can add to the head or add to the tail, so those could change. But the head, the beginning, the tail, the end, what you are adding to the tail always in a singly linked list. When the linked list is empty, when there is nothing in the linked list, when there are no nodes in the linked list, the head and the tail are also empty. When a linked list only contains one element, the head and the tail will reference the same node. So if there's a single element, it serves as both the head and the tail, and then the next time we add an element, that will become the tail. Anybody have any questions? I'm going to actually just drop an anonymous poll since I haven't done one yet today. Anybody have any questions about anything we've covered today, anything from the videos, anything up to what we've talked about on linked lists? No, everybody vote quick while y'all are doing that. All right, no questions, so we will move on. And I'm just going to, while we're doing this, okay, so if we had a linked list, and let's say it was a new linked list, remember we described how the head and the tail, head and the tail, I know that's horrible, but how these are both empty. So remember that when we implement a linked list, you're actually going to have in the class that we use, like we will be using Python classes for all of our data structure implementations, just like we've been very class heavy the entire time because we're going over OOP. They're used a lot in Python, and they're very specific. They're specifically suited to implementing data structures, or well suited, not specifically, but they're well suited for implementing data structures. So if you had a new linked list and you had a head and a tail, and those are both empty at this point, they have no value because it's an empty linked list. If you perform the operation, if you added to the head, what would happen? Somebody can get on the mic so you didn't have to. If you added to the head, what happens? You have a linked list. Remember, a linked list has a head and a tail. When the linked list is empty, those both are none, null. So if you add to the head, what happens? Head will be the value you insert, tail will be null. Yes, the head will be the value you insert, but remember then, and this is why I'm kind of going over these to try to reiterate these, remember that when you add to the head, now you have a single element. When there's a single element in a linked list, both the head and the tail are that single element. You're asking why the head and the tail point to the same element? To be honest, other than saying it's specific to the linked list, I don't have an answer off the top of my head. I have a suspicion, but I'm not 100% sure of it, so I don't want to say it. That would be a great question for the QA, or something I can research afterwards to make sure that I'm thinking correctly. But it's going to have to do with the underlying data structure itself. But yeah, that would just be a good one to bring up later. For now, just know that when we've inserted that single element, now we have one node in that linked list in both. So we have that one node that both the head and the tail are pointing to. Yeah. And so then if we added, in this case, if we added to the tail, then what would happen? If we added to the tail, what would happen? If we add to the tail, remember the tail is what typically you add to at the end. That's the end of the list. The head is the first item in the list. Head will point. Tail will point to null. Now that I'm rereading, yeah, perfect answer. Actually, the head will point to tail, and the tail then points to null. Because remember, we have that null at the end of all of them. So yes, the head will point to tail. The tail will point to null. The head is now the head. The tail is now its own element. So we have two elements. We have the head, and we have the tail. Head, tail, and then null. And if you add to the tail again, what happens? If you add to the tail again, what happens? Last question like this, but if you add to the tail, what happens? A new tail is created and the one before will point to it. Exactly, exactly. So. And so whether you're adding, and that's the whole point of what I was trying to cover here mostly is everything's going to follow that same type of logic that as far as the pointers go. Remember, we only have a pointer to the next. Remember the rule that if it's empty, then the head and the tail are null. If there's one element, the head and tail both point to it. And then as we start to add elements, typically to the tail, then the previous tail will point to the new tail. And we'll see that more as we're actually implementing these and working through these. But I'm going to give everybody a 5-minute break right now. So come back about 2 after the hour. So 10:02 Lambda time, 2 after the hour. And we will start with the coding at that point. Anybody have any questions? Think of them over the next 5 minutes. You can add them up to the poll right here and add any questions that you may have that you may think of. Okay, everybody should be back now. Anybody come up with any questions they want to add? Start typing now or add them up to the comments. Otherwise, we are going to get started with the code for today. And in doing that, I'm going to try to stop at times to ask for what maybe we should do, what we should be coding, why we're doing something to help reinforce the principles that we already discussed of how linked lists behave, and of course for the exercise in using Python, which is still pretty new to most of us. So that said about linked lists and questions. I don't see any questions. Like I said, we're going to use a class for everything we do in data structures for Python. Will be written in a class here at Lambda, at least. So the first class that I would want to implement would be for a node. Can anyone tell me why it's ideal to implement these with classes in, we'll say, in Python? Why is it ideal to implement these data structures in classes? What are classes good for? What's a fact about a class, something that's inherent to a class that makes it nice for using with these data structures? Yeah, it's reusable. Exactly. So we just have to keep calling instances of this class. So if we want to make a new node, we just call a new instance of that node. If we're going to make a linked list, it's obviously you're going to have the nodes as part of that linked list. And then that class of linked list, the next time you need a new linked list, you just reuse that. And then all the functions are built into it as methods. But yeah, great answer. So we'll have a class of node, have our classic init. We're going to have self and value equals none. Next node equals none. The value, just as we talked about earlier, is going to be whatever primitive or object that you're putting into that node, the data that you're storing, the data point that node is, and the next being the reference to the next, like we talked about in the lecture leading up to this. Can anyone tell me why we have equals none? What does this serve to do in Python? Null. Well, no, but there's a more specific. Yeah, that's none, null. Different languages, different words, but yeah, if you don't give it a value, it's going to throw an exception if you don't supply an argument in, if you just put value comma next node and close the parens and didn't have the equals none. You're just setting a default for it, and you can do this with anything. You could set the default, the value equal to 1 if you wanted, or anything you wanted. So those are just default values, and you can always use those in Python. So here we'll just say self.value equals the value that we took in. What else would we need to do? What else do we need to have inside this init? What else are we doing? Trying to store. Yeah, the next node. So self.next node equals the parameter. Then we will define a few methods for this. If we wanted to just say get value, what would we do here? If you just wanted to get the value of this node, this getter function, what simple operation, one-liner do we need to do? If we're trying to access the value of this node, what would this method need to do? Well, we've been working on this stuff. Been in the language a while. If we wanted to get the value that we've passed in here, self.value, with this getter function, what do we need to do? Return something? What would we return? One line. Yep. Turn self.value. And the same if we were going to define a get next. We'd just return self.next node. And then if we wanted a setter function here called setNext, what other parameter would we need besides the ubiquitous self? We would need to take in something for setNext. What would we need to take in as an argument for this setter function, setNext? Dan Wrong is typing. What would we need? Said get next. Yeah, not get next, but we call it something like new next. Because you've got to supply the new next that you are setting. So all you need is the new next. And for here, all you'd be doing is, actually don't even have a return, self.next node equals new next. Forgot my colon here. So all this is doing is setting the value next node and this setter function, and it's setting it to the new next that you supplied to it. Shouldn't what be opposite? No.
So I get confused why we set what's inside the new nest and why we set that to the last load.
Okay, so I think I know what you're asking here. So say we have an added D here that we've got up on the screen. So right here, C points to null.
Mm-hmm.
Now, when we add D, remember now C will point to D.
Mm-hmm.
So we have to be able to set the next value. We have to remember in object-oriented programming. I was going to use this as a question for y'all, but I'll just cover it now. Remember I was talking earlier about the getter functions and the setter functions so that we're not directly accessing variables. And a lot of times, if you're working with private variables, it's just a practice to do it like that. So this setter function is just serving to change the value here of next, the next node, from null to D when you add D here. So we take in a value for the new next, which is the D, the pointer to D, and then we're just setting the next node, the value here that was originally pointing to null in the example, to the new next, to D. Does that make sense? Cool. All right. So we're going to make a second class now for the linked list itself. And we'll have to have our init. And when you're making a new linked list, you don't have any parameters that you're adding. You're simply creating a linked list. So remember, a linked list has two things. So what do we need to do here? Look up earlier, we were doing a self dot something. We were setting some things. What do we need to do here? Tell me in terms of the code, or you can tell me just in pseudocode. What are we doing here? Data and pointer. Remember, this is now talking about the linked list. That for the node, yeah, we had to take in the data, the value, and the pointer, the next node. For the linked list, remember when we make a linked list, we just have an empty linked list. Yeah, a head and a tail. So you just say self.head, and what's it equal to? What are both of these equal to? We didn't have to take anything in, so logically, what are these equal to? And based on what yeah, none. So when we create a new linked list, we have this object that is just holding the head and the tail, and they reference none, as we discussed earlier when I was asking what happens when we have an empty linked list, and I referred back to the fact that each of them that was the head and the tail were none when you had an empty linked list. So when you instantiate a linked list, you are simply giving it a head, an object with a head and a tail that both are equal to none. They're empty. So if we wanted to define a method, add to tail, we would obviously want to take in the value that we're going to add. All right. What would be the first thing we would want to do here? If we're going to add to the tail, we're adding something new to the linked list. So we need to make something here. I'm trying to word it so I don't give away the answer. Somebody, what do we need to do? If you're going to add to the tail, what should we do? Set tail equals value. No, what I was thinking of here is, remember, we've got a node class. So if we're going to add a value and you've taken in that value, the first thing we're going to do is instantiate a new node with the value and none for next node. None because it is the new tail. And then I'm going to do a specific check and say, if not, and if we're adding to the tail, think about you can add to the tail at any point. Even a brand new linked list, you could invoke add to tail, an empty linked list. So what is something we would want to check for here in this logic statement that I've started? If not, if not, what am I looking for? If it doesn't exist, we need to do something specific. What do we need to look for to make sure it exists or doesn't exist? What would be the one thing we would need to look for in this linked list when we're adding to tail? Maybe we would want to, Yanron's typing, so let me see what he says. Well, actually, yeah, you're close, but what we want to look for is the head. Remember that if the linked list is empty, there's no head and no tails. So we would say, if not self.head, then if there's no head, we'll set the head equal to the new node. And what do we set the tail to? What do we set the tail to? If there's no head, that means we have an empty linked list. Remember, the head is the beginning of that list. What do we set the tail to? Yeah, set to new node as well. Because remember, both the head and the tail in a single element will point to it. So if there's no head, there's obviously no tail. It's an empty linked list. So if it's an empty linked list, we set the head to the new node and the tail to the new node that we've instantiated. And then we'll just come out of this and say else, if the head already exists, else, what do we want to do to the tail? The head exists, so the tail, whether it's many, many units of data later, or whether it's a linked list with two elements in it, a head and a tail. Let's say we have a head and a tail now, or it just had a head. What would we want to do to the tail? Look at the other things that we have X. What would we want to do to the tail here? We've already worked on part of this. Self.tail, tell me what to invoke. I can invoke a function here. Yanrong is typing. Set to null. Remember, the tail is actually the last element in that array. In that linked list. It's the last node in that linked list. That in itself points to none, to null. So what we're going to do here is say, but we just use that setter function that we have here. And we set the next to the new node. And what's self.tail equal to now? We've taken the old tail and pointed to the new tail. which is the new node. And the new tail, therefore, is also new node. Any questions there? All right, so the next thing we're going to do, the next method that we're going to add here, and you're going to be doing a lot more of this in your independent project, but this is just trying to give you an idea of how we're going to work with these data structures and give you a little bit to work with, and something, like I said earlier, to be able to reinforce the principles that we discussed about data structures, about linked lists, when I had to talk on and on at the beginning of the GP today. So if we wanted to remove the head, remember, the head on this singly linked list being the first element, the head that points to the next element, that points to the next, points to the next. Finally, this is the tail. The tail points to null. So if we wanted to remove the head, what would be the first thing maybe we would want to check for before we did anything else? What would be the first thing to check for if we wanted to remove the head? Think logically here and not even programmatically. If we wanted to remove the head, what's the first thing we might want to check for? Or check for, yeah, if there's a head. So if not, self.head, we'll just return none. Okay, so we've covered the, not even the edge case, but the possibility that there could be no head. We could have all of these methods available that could be called because we could have just instantiated an empty linked list. So before anything's in there, we could call this method. Excuse me. So we've checked to see if there's a head. Now what else would we want to do? No, not remove head, but good thought. What we're going to look for is an action. So we're going to say if not self dot head dot get next. And what this is allowing us to do is we're just calling on the head. Since we now know the head exists, the second check that we're doing here is we're seeing, is there a next element? Not necessarily is there a tail, because it may be much more than in between the head and the tail. We're just saying, is this a single element linked list, or is there a next element, be it the tail or be it just another node, another value in that linked list. So if it's a singly linked list with one element and it does not return true for anything get next, and it's going to just return none, what do we do here? Almost. So almost, yeah, I'm wrong. We're going to say head equals self.head. We are going self.head equals an n. So you had almost everything there besides actually the first line 36. So like I said, great. You had everything right. It was just self.tail equals none. and we will return head.get value. Otherwise, we have more than one element in our linked list, and in that case, we can just say value equals self.head.get value, and we can say self.head equals self.head.get next. And return the value. Any questions on removing the head? We check to see if there's an empty linked list by seeing if there is a self.head. If there's not a self.head, we simply return none. If it's a single element linked list, we say in the if not self.head.get next, we set the head to self.head. Then we say self.head equals none, self.tail equals none. Return head.get value. And then if we have a regular linked list, or probably more times than not, a linked list that has more than a head and a tail, so there is that next value, then we simply set value to self.head.get value, self.head equals self.head.get next, and we return the value. Any questions up to this point? We're going to implement one more, just a contains, to be like a search that we were talking about earlier. Everybody vote, and we will five no's. So for the last, so the first thing we're going to do is going to see if there's a head. If there's not a head, that means no matter what, it's an empty linked list and we can return false. That's the quickest way to just say, is this linked list empty? Is to check to see if there's not a head. So if there's a contains and the linked list, no matter what the value is looking for, if there's not a head, we simply return false. And then we're going to set an iterator here, if you want to think of it that way, and we'll say current equals self.head. Why do we need to have an iterator, as I referred to it, or why do we need to start at a certain point where we have a method that we can give it a value? Say we have a linked list with 100,000 elements in it, and we are looking for a specific value to see if one of those nodes contains that value. What are we going to have to do to find that, whether that condition exists or not? Got a linked list. Remember how a linked list works and how we reference items in a linked list. Singly linked list only has a reference to the next item, which only has a reference to the next. In the singly linked list, there's no reference to the previous. So therefore, what are we needing to set an iterator for? What do we have to do to this linked list to see if it contains something? And wrong, thank you. Access to value. Not quite sure what you're meaning by that, but we have to iterate over this linked list to check. We're going to have to check each node in the linked list. Is this the value? Is this the value? Is this the value? It's kind of like when you're trying to see if an array contains something. In this case, we want to know, does this linked list contain anything that we are asking for in the value? So we've got to iterate over it. So we will just start at the head since that's the beginning of the linked list. And next thing we're going to do is have a while loop. And we will say while current. And we will say if current dot get value equals value, we return true. So we're just calling the get value method on current being a node. In this case, the first node, the head. And while it's current, if we say get value, it's the value, we simply return true. And then if it's not true, we need to move on to the next node. So we would say current is, what do we do here? We need to iterate the current up. So what do we set the current to? Yep, exactly, Yanron, get next. And then if we've gotten through all of this and we've gotten kicked out of the while loop because there's the current eventually will point, what would the current eventually point to if we're iterated all the way through? And then what would the current finally get to? Yeah, it would get to null. It would get to none, and that would kick us out of this loop because while current is just evaluating a Boolean, and Boolean evaluates as false here in Python, of course. So that none will turn that Boolean to false and kicks out of the loop. So what would be the very last thing we would want to do here after with a loop? We're going to return something. What would we return? Yeah, return false. Yeah, and run. Let's see what you're typing. Oh, what did I? Gotcha. Thank you, Yanrong. And anytime, I think I've told y'all before, but anytime you see me and you think that I've messed up somewhere or something's missing, like I said, I tend to leave a lot of the colons off at times. But if anybody sees anything that I'm doing, feel free to point it out. And thank you for that. So yeah, that's all we got to do. So in the contains, we're just going to say if there's not a head, we return a false because it doesn't contain anything because it's an empty linked list. Then we start the iterator. We're going to have to iterate over the linked list one at a time using the next pointer to move to the next item. So we'll set it to the head, and then we're just going to say while current. If current.get value is the value, we return true. If the current value is what we're looking for, we indeed return true. If not, then we set the current equal to the current.getNext, which simply moves to the next item on the linked list. And if that's the next item, the while loop runs again. If there is no next item, then it will kick us out of the while loop. And we simply return false because we went through the entire linked list and did not find the value. Anybody have any questions? I'm going to make one more poll. Anybody have any questions about anything we've gone over, specifically this last method that we've gone over? All right, any questions? Everybody have the link to your repo for today. Anybody need the link to the repo? Yeah, it's the regular one. I'm just making sure everybody has it. Yep. And that will be your repo for the entire week. So just know that most of the time we have the entire week will be data structures for the subject, as was reflected in the change today that Josh made. And the entire week will be one repo and then a regular sprint at the end of this week. You're saying for the assignment today, you're doing just the cues? Yanron? Yes, today's MVP is the queue. Today's MVP is the queue. Obviously, if you get done with the MVP for today, move on to doubly linked lists. Start doing the reading for it. Start doing the work on it. If you want to move on to doubly linked lists and you need more reference on how to investigate or where to look in the TK, some extra material, just DM me. I'd be happy to supply you with anything. Anybody have any overall questions? It's about 15 before your lunch. I'm going to go ahead and let everybody yeah, I'm going to let everybody get out of here. Remember that regular workflow. So fork it, clone it locally, make your branch, make your change, push up, make a pull request, and add your PM as a collaborator. And if you're in my PM group, get those done quickly, please. And I'll be checking for them, looking for them in the email. And I think that's all I've got. So take a break, go to lunch. I will post the video. I will drop the code in the channel as well that we did today so that you have that as a reference. And thank you, everybody. And that's all I've got for you.